imagine teaching a computer to paint and it suddenly insists on copying your photo album instead of inventing something new. That's the puzzle with diffusion models. In theory, the best mathematical denoiser should just memorize the training set. But in practice, these models create fresh images. So what's going on? This new study digs into the mystery and finds that the secret sauce isn't hidden in the neural network's architecture. Instead, it's in the data itself. Pixel correlations, the way nearby or even distant parts of an image line up, naturally create the sense of locality. By analyzing this with a classic tool called the Wiener filter, the researchers show that data statistics, not convolutional tricks, explain why diffusion models generalize. It's like discovering that the style of the painting comes more from the canvas than the brush.
All right, so this paper kicks off by tackling a really interesting paradox in diffusion models. On one hand, you have this theoretical optimal denoiser. Think of it as a perfect mathematical solution that's designed to be the best possible at the training task. But here's the problem. In practice, this optimal denoiser just ends up memorizing the training data. It can't generate anything new, which, is the whole point of a generative model. On the other hand, we have the deep learning models we actually use, like UNets. These things work incredibly well, generating novel, high-quality images. So what's going on here? What explains this huge gap between the perfect but useless theory and the imperfect but useful models we have in practice? Well, the common explanation has always been that the UNets architecture is the secret sauce. The idea is that its built-in assumptions, like locality from its convolutional layers, act as inductive biases. These biases are thought to stop the model from just memorizing everything, and instead guide it toward generalizing to new images. But this paper proposes a totally different idea. It argues that the locality we see in diffusion models isn't some special gift from the CNN architecture. Instead, it emerges naturally from the statistics of the image data itself. The authors suggest that even a simple linear denoiser will show this same local behavior, just because of how pixels in natural images are correlated. And they plan to prove this with both theory and experiments. So building on that idea, the paper continues by challenging the conventional wisdom that a UNets architecture is the key to its success. They point out a weakness in previous theories. Those theories had to first measure properties of an already trained UNet, like its receptive field, and then plug those numbers into their analytical models. This paper wants to derive everything from first principles, without peeking at the UNet's homework. Their big idea is that the data itself is what dictates how the model should behave. For example, if you train on a dataset like CIFAR10, where patterns are small and repetitive, the model learns a very local behavior. But if you switch to a dataset of faces like CelebA-HQ, the model learns non-local patterns to connect features, like the two eyes. This strongly suggests the data, not the architecture, is really in the driver's seat. They then lay out their main contributions. First, they're going to show that these sensitivities are learned, not hard-coded. Second, they'll create a simple linear filter based on classic signal processing ideas that behaves just like a complex neural network. And third, they'll prove that their simple filter actually explains the UNet's predictions better than previous, more complicated analytical models. To get started, the paper lays some groundwork with preliminaries. It introduces the core concept of the diffusion forward process. This is basically how you create the training data. Imagine taking a clean image and gradually adding static to it over time. The formula you see here is the precise recipe for that process. It tells you exactly how much of the original image and how much random noise to mix together at any given time step to create a corrupted image. The entire goal of the diffusion model is to learn how to perfectly reverse this recipe. Alright, so if that's the recipe for adding noise, what's the goal for the model? This page gets into the mathematical weeds to explain just that. First, it lays out the standard training goal for a diffusion model. The formula here basically just says, train a network that takes a noisy image as input and tries to predict the original, clean version. The better the prediction, the lower the loss. Simple enough. Next, it introduces that optimal denoiser we talked about. This is the perfect theoretical solution. It's defined as the average of all possible clean images that could have resulted in the noisy image you're seeing. But when you only have a finite dataset, this optimal denoiser becomes something else. It turns into a weighted average of all your training images. And here's the crucial part. The weight for each training image is determined by how similar it is to your noisy input. As the noise level drops, this system becomes a winner-take-all competition. The single closest training image gets all the weight, and the model just spits out a copy of it. This is the mathematical root of that memorization problem. So, how did previous work try to fix this? A popular idea was to force the model to behave like a CNN by adding constraints. They modified the training objective with two new rules. The first is locality, which tells the model it can only look at a small patch of pixels to predict a single pixel. The second is equivariance, which means if you shift the input image, the output should shift in the same way. This is that inductive bias argument that this paper is about to challenge. So let's take a closer look at how that inductive bias approach actually works. The formula here unpacks the math. Instead of comparing a whole noisy image to whole training images, it operates on a patch-by-patch basis. To denoise a single pixel, it looks at the small patch of the input image around it. Then, it searches through the entire training dataset, every image, and every possible shifted version of that image to find the single best matching patch. The prediction is then based on this nearest neighbor patch. This is how those models force locality into the system. But the paper then pivots, suggesting there's a better way. It notes that other research has found that at high noise levels, complex diffusion models start to behave like simple, linear filters. This hints that maybe we don't need all this complicated patch-matching machinery after all. This leads us to the core section of the paper, deriving the model's behavior from data statistics. They introduce a key concept called sampling voids. Think of it this way. A trained model only ever sees noisy versions of its training data. Any new image, especially one with low noise, exists in a void where the model has no training examples. How the model behaves in these voids is what determines if it can generalize and create new things. The old optimal denoiser fails here. It has what they call a teleporting behavior. If you give it a new image in a sampling void, it just finds the closest image it remembers from training and snaps to it. This completely kills novelty. The authors argue that a good denoiser needs a pass-through property, which would allow the unique features of the new input to survive the denoising process. This next page brings that exact idea to life with a really clear figure. If you look at the first panel, it shows a diagram of these sampling voids. Imagine that every image in your training set creates a cone of noisy versions of itself. A trained model is comfortable inside these cones, but a new test image lives in the empty space between them, a void, where the model has no direct training experience. Now look at the middle panel. It shows what happens in this void. When a trained UNet gets a slightly noisy new image, it correctly cleans it up, preserving the image's identity. This is the pass-through behavior we want. But the so-called optimal denoiser does something totally different. It sees the new noisy image, panics, and just finds the closest image it remembers from its training set. It essentially teleports the input to a known location, completely failing to generalize. So, how can we build a model that has this good pass-through property? The paper proposes using the data's statistics. The key idea is to look at the principal components of the dataset, the most fundamental patterns. When you add noise, patterns with a high signal-to-noise ratio, which we'll call SNR from now on, survive, while weak patterns get drowned out. This leads them to their main proposal, the Wiener filter. This is a classic, simple linear filter defined by the formula you see here. All it does is look at each principal component of the input and decide how much to keep based on its SNR. If a component is strong compared to the noise, it passes through. If it's weak, it gets filtered out. This simple, data-driven mechanism perfectly explains the desired behavior without needing any complex, handcrafted rules about locality. Okay, so we have this idea of a pass-through property, driven by a Wiener filter. But how does this connect back to our original question about locality? Well, the paper dives into the math of what they call sensitivity fields. A sensitivity field for a pixel tells you which parts of the input image the model looked at to decide that pixel's final color. Previous work just assumed these fields were small, square patches, basically hard-coding locality. This paper argues that's way too simple. They show that for their proposed Wiener filter, the sensitivity field isn't a fixed patch at all. Instead, its shape and behavior are determined entirely by the SNR of the data's principal components. The formula here is key. It shows that as the noise gets very low, the sensitivity field essentially becomes an identity map. This means the model just copies the input to the output, the perfect pass-through behavior needed for generalizations. Crucially, this means the exact shape of the sensitivity field is a function of the asterisk data, not the model's architecture. This is their central claim in mathematical form. So how are they going to prove all this? Well, they lay out a three-part plan. First, they'll show that different architectures, like UNets and transformers, all learn similar sensitivity fields that match the data's statistics. Second, they'll manipulate the data's statistics to show they can force the model's sensitivity to take on any shape they want. And finally, they'll use these insights to build a better analytical model that outperforms the previous patch-based approaches. And this is where the paper really starts to present its most compelling evidence. Take a look at Figure 2. It's the first big punch. It compares what a diffusion transformer, a UNet, and their own simple Wiener filter see when denoising an image from CelebA-HQ. Now, a UNet is built to be local, while a transformer can look anywhere it wants. But the amazing result is that they both learn the exact same thing, a tight, local sensitivity pattern, and this pattern is perfectly predicted by their Wiener filter, which knows nothing about architecture and only knows about the data's statistics. This is a huge finding. It shows that the data is forcing both models, regardless of their design, to behave locally. But then they ask, what if the data asterisk isn't times local? That's where Figure 3 comes in, and it's a fantastic counterexample. They switch to a data set of aligned faces. Now, when the model is asked to denoise a pixel on the left eye, it doesn't just look locally. The sensitivity map lights up over times both eyes. The model has learned the statistical fact that eyes come in pairs and is using information from the right eye to help fix the left one. This is a non-local, structured pattern that emerged purely from the data. Finally, they state their ultimate proof. They claim that by manipulating the dataset's statistics, they can actually force a UNet to learn any sensitivity pattern they want, even non-local ones. This is the final nail in the coffin for the architecture as king argument. The data is clearly the one in charge. This next page delivers what you could call the experimental knockout punch. The authors conduct a brilliant experiment to prove their point. They take the CelebA-HQ dataset and artificially add a new statistical correlation to every single image, a faint pattern in the shape of the letter W. Then they train a standard UNet on this modified data. The result, shown in Figure 4, is incredible. The top row shows the normal, blob-like sensitivity the UNet learns on regular CelebA-HQ. But check out the bottom row. This is what it learns on the W data. The sensitivity field is no longer a blob. It's a perfect W. They literally forced a convolutional network, which is supposed to be local, to learn a non-local, arbitrary shape just by changing the data. This is definitive proof that data statistics, not architectural bias, are in control. Building on this powerful insight, they propose their new analytical model. They argue that previous models were on the right track, but used the wrong tool. Those models used a rigid, square-shaped mask to enforce locality. The authors basically say, let's replace that dumb square with a smart, data-driven mask. Their new model, described in the final formula, does exactly that. It's still a nearest neighbor-style denoiser, but its sense of distance is now guided by the sensitivity field of the Wiener filter. This means the model's idea of locality is flexible and adapts to the dataset, whether it's the simple blobs of CelebA-HQ or the complex eye-to-eye connection in faces. It's a simple swap, but it's based on a much deeper understanding of what's really going on. So does this new analytical model actually work better? Let's look at the results. Figure 5 here is the big payoff. It's a side-by-side comparison of images generated by different models across 5 datasets. The top 2 rows are the gold standard. That's what a real trained neural network produces. The goal for the other analytical models is to get as close to that as possible. And the author's model, in the hours row, clearly wins. The most dramatic example is on the CelebA-HQ faces. The competing models from prior work, which assume a simple square patch for locality, produce these blurry messes. They completely lose the eyes and facial structure. But the author's model, using its flexible, data-driven locality, generates faces that are much sharper and more realistic. It understood that non-local connection between the eyes and preserved it. The paper then lists the key advantages of their approach. First, it's more interpretable, because it's built directly from data statistics, not by trying to copy a trained network. Second, They don't force the model to assume that patterns are the same everywhere in the image, which is a bad assumption for datasets like faces. And third, their model's sense of locality is specific to each pixel, making it far more powerful. In the end, the visual and quantitative results all point to the same conclusion. Their model works better because it correctly captures the true locality of the data. This confirms their hypothesis. The secret to a good analytical model isn't to mimic a CNN's architecture, but to mimic the data's statistics. And this final page brings it all home with the hard numbers. If the pictures weren't convincing enough, check out Table 1's. This is the quantitative proof for everything we've just seen. It measures how well each analytical model can replicate the output of a real, trained diffusion model. The two key metrics are the R-squared metric, where higher is better, and mean squared error, where lower is better. The results are crystal clear. The author's model, highlighted in green, is the undisputed winner among all the analytical approaches. It consistently gets the best scores on every single dataset. The most telling result is on the CelebA-HQ faces dataset. Their model achieves an R-squared metric score of over 0.9, which is a massive leap over the competitors who are stuck down in the 0.7es. This numerically proves that their data-driven approach to locality is essential for handling complex data. The paper then wraps up in the conclusion. They restate their core finding. Locality in diffusion models is a property of the data, not the architecture. They walked us through the evidence. From showing that UNets and transformers learn the same local patterns on CIFAR10, to demonstrating they could force a UNet to learn a W shape just by manipulating the data. They acknowledge the limitations, noting their work focuses on the simpler, linear aspects of these models. But they've successfully explained the pass-through behavior that allows diffusion models to generalize. They've built a better analytical model and, most importantly, shifted our understanding of why these powerful models work the way they do. Thanks for joining us today. Happy exploring together.